Okay, so picking up where we left off last time, if we can kind of power through this stuff so we can start getting into some of the game programming stuff. We had mentioned that there's two kinds of programming languages, loosely typed and strongly typed, where loosely typed languages do not require us to dictate the kind of value we're going to store in a container. Strongly typed languages do. So then we dove into this idea of variables, which is our named containers for holding values. And this is what I just said, the loosely typed versus strongly typed. So variables are how we mimic memory, is one of the ways the human beings solve problems. We looked at the syntax in a general programming language for, well, that is a language based off of the C programming language. So if we go back to our lineage here, languages are based off of this guy, have this syntax for creating variables. The type followed by the variable name equals the value. All right. So where we left off was this discussion about types. What are the various types built into languages? So I'm going to talk about the types that are built into C, C++, C#, Objective-C, and Java, which are all the same types. And we'll see that GameSalad, the tool we use in here, uses a subset of those types, but learning about those types will make enough sense to us. So, built into Java, we have a byte, short, int, long, char, float, double, and Boolean. All right. So we're going to talk about each of these. Now bytes hold whole integers. It's the kind of value a byte holds. A short holds whole integers. An int holds whole integers. A long holds whole integers. A char holds whole integers. A float hold decimal point values. A double holds decimal point values. And a Boolean holds whole integers. All right, so these are the types of variables, the types of containers we have in our modern programming languages. So the types that, well, let me say that again. These are the types that are built into our modern programming languages. So I'm going to actually expand on this word types up here and say this is our primitive types. That is, types that are built into the language for our use. Okay? GameSalad, the tool we're going to use in here, has a subset of these, and I think that'll make sense here in a few minutes after we talk about, hopefully some of you are questioning why there are so many ways of holding whole integers. All right, how many of you have heard of the Y2k bug? Okay, anybody know what the Y2k bug is? Versus just hearing about it? Go ahead.
1999, like when the millennia ended, or the new one started, people thought that all computers were just going to die and it was going to be like the end of the world.
Okay, do you know why? Why they think there was going to be a problem? Go ahead.
Because it was going to crash the computers that held the launch codes for nuclear missiles and all the nuclear missiles.
Okay, but do you know why it was going to crash those? All right, so you just told a much more dangerous version of his story. Okay, stuff is going to explode. Oh, you gotta follow up?
It's because the years didn't go past 1999. Is how it was.
Okay, it's related to that. All right, so let me tell a little backstory then. Memory. Famous quote. Anybody know who said that? You will never need more than 32K of memory. This is kilobytes of memory. Bill Gates. Bill Gates, Microsoft dude. Okay, founded Microsoft. Okay. How many of you have computers, either laptops or desktops in here? Most of us, right? All right. So, everybody put their hand up. So we're gonna, as technologists, we have to know how much memory we have in our computers. So as soon as I get to an amount of RAM that's more than you have, put your hand down. Okay, so 1 gigabyte. Most of you have that. 4 gigabytes. 8 gigabytes. Probably gonna lose a bunch there. Now memory is not hard drive. Memory is the amount of RAM in our computer. Okay, 16 gigabytes. Okay, we lost everybody except 1, 32 gigabytes. Now we lost you. Okay, so most RAM we have in any of our computers in here is 16 gigabytes. Seems like a lot of you had 8 gigabytes. So a lot of you have newer machines. Okay, fair enough. So how much bigger is 8 gigabytes than 32 kilobytes? It's actually an interesting question. A lot of us kind of know of these buzzwords. But how do megabytes and gigabytes and kilobytes, how do all these things connect? So we're going to create a little chart here. We're going to call this guy bits and bytes. That's a fun chart. And it's very related to what we're about to talk about. So what's a bit? Bit is a 0 or a 1. Okay, that's what a bit is. A byte is 8 bits. A kilobit, KB, is, anybody know? 1024 bits. A kilobyte, K big B, or sometimes shown as big K, big B, the important part being the big B, is 1024 bytes. Megabit is 1024 kilobits. Megabyte is 1024 kilobytes. Gigabit is 1024 megabits. Gigabyte is 1024 megabytes. Terabit is 1024 gigabits. And a terabyte is 1024 gigabytes. So that pretty much takes us up to our current sizes that reference things relative to computers. Next one is exabytes. So, some interesting things for us to consider. How many of you have internet at home? Most of us, right? How many of you know the speed of your internet? 3.5 people? Okay. As technologists, we should all know the capabilities of our technology, right? Okay. So those of you who, the 3.5 people who know what the speed of your internet is, you mentioned you do, right? What's the speed of your internet?
Well, it depends on the day.
What's the advertised speed that they sold you?
The advertised like 30 down and like 5 up.
Okay, so 30 megabits down, so you have cable.
Yeah.
Okay. So you said depends on the day.
Yeah.
Tell me about that.
I mean, sometimes it's like 5 down and like 3 up.
Okay. Well, does that mean they're lying to you about your internet?
No.
What does it mean?
It means like we have terrible connection.
Well,
I think.
if you have a 30 megabit per second internet connection, but you're only getting 5 down, that could mean that the person you're downloading from can only give it to you at 5. Make sense? So, so those of you who have these really fast internet connections, very rarely are you going to maximize your internet connection. Modernly, the idea is that You might have lots of things going on in the house that use your internet connection. You might be streaming Netflix in one room, playing a video game, watching YouTube, downloading a big file, probably an illegal movie, or music, one of the two, right? So you're doing lots of internet-y stuff in the house, and each one of those takes up a chunk of your bandwidth. Now, there's some tools out there that allow you to open up multiple connections to a download server that try to maximize your download speed or maximize your internet speed. But keep in mind that your download is somebody else's upload. You mentioned that you have 30 megabit down by, like you said, probably 5 up. Okay, realistically speaking, you're probably not downloading from somebody else who has a cable modem. You're probably downloading from somebody's server, Apple or Google or something like that. They have what's known as a synchronous internet connection, same speed up and down. They don't want you running a server out of your house, which is why the upload is slower than your download. They want you to be able to digest data but not send a whole lot of data. Because really, you're only using your upload for requesting websites and like doing email attachments. That's the main thing you're using your upload for. Or I suspect in your case, seeding the BitTorrent network. Never heard of BitTorrent? I don't believe him. Historically, people who know the speed of their internet connection also are very well versed with BitTorrent. But you probably don't spend too much time seeding it. Once you've acquired what you want, you turn it off, right? Yeah. You're a leecher. Yeah, makes sense. All right. So in any case, his internet connection was advertised to him as 30 megabit per second. This side, not megabyte per second. So mathematically, 30 divided by 8, the maximum speed you could ever download something at is 3.75 megabytes per second. That's the maximum potential speed you can download stuff. 3.75 megabytes per second. Or, times 1,024, 3,840 kilobytes per second. Make sense? All right, so our internet speeds are advertised to us in megabits per second, but most consumers think it's that. Sometimes the people you're buying the internet from just say megs. It's a 30 meg internet connection. Okay? Megabytes are bigger than megabits by a factor of 8. Okay? When you buy a hard drive, it's measured in gigabytes or, more modernly, terabytes. That make sense? All right. But in any case, here's kind of our chart for these different size things. So it's important what the B is. If it's a little b, it's over on this side. If it's a big B, it's over on this side. So if you want to convert megabits to megabytes, you can take the shortcut and just divide by 8, because there's 8 bits in 1 byte. Or you can walk your way up the chart. So a megabyte times 1,024 times 1,024, then times 8 divided by to get you down to your speed. Okay, but this is our chart for bits and bytes. And as I said over here, where did I say it? Here. You will never need more than 32 kilobytes of memory. And as we polled the class, it seems like the average in here is about 8 gigabytes of memory. Right? Pretty high average though, so a lot of you have fairly new computers. Typically, I would say if I were making a guess at kind of the average amount of RAM in most computers today, it would be 4 gigabytes. So memory is the amount of RAM. Hard drive space is the usually the bigger number. You have a 2 terabyte hard drive or something like that. Okay, so if 32 kilobytes is what we have today, is what Bill Gates said we'll never need more of. And we have 8 gigabytes today. So that's 8 times 1,024, that's in megabytes, times 1,024, that's in kilobytes. So we have 8,388,608 kilobytes of RAM today. So let's divide that by 32. So we have 262,144 times the amount of memory that Bill Gates told us we would ever need. He was off by a little. Make sense? Couple 100,000 times off, no biggie. No biggie, right? Okay, so he made this quote in a much different time. Memory used to be very, very, very expensive. For those of you, anybody in here who said they had 8 gigabytes, any of you start with 4 and upgrade to 8? Okay, how much did that cost? $40. Okay, not a lot. It's not very expensive. It's the punchline. Okay, so he doubled his amount of memory, doubled it for $40. Okay, and had you really shopped around, you probably could have even gone cheaper, but not expensive in the big scheme of things, right? In 1996, I had a computer that had 8 megabytes of memory in it. And I upgraded it to 16 megabytes of memory. Okay, now, just to do the math, you paid $40 for 4 gigabytes, right? So we have 4 gigabytes times 1,024, that's megabytes. Okay, so you paid $40 for 4,096. So we're going to divide that. Well, we're going to say 40 divided by 4,096, and that's $0.009 per megabyte. So times 100. Actually, no, it's 9 cents per. Yeah, it's 9 cents per. So you pay 9 cents per megabyte to do your upgrade. Fair enough. Well, back in 1996, I bought an 8 megabyte upgrade chip. How much do you think that chip cost? $60? $1,000. $1,000 to go from 8 megabytes to 16 megabytes. Okay, so I paid 1,000 divided by 8. I paid $125 per megabyte. $125 per megabyte, slightly more than you paid, right? So $125 times 100, that's 12,500 cents. Divide that by 9. 1,388 times what you spent per megabyte. Close. Right? These are all rounding errors, right? Okay. Memory used to be very expensive. Very expensive. And before that, it was even more expensive. Okay, so that was somewhere in the, I don't know, maybe not middle, but certainly 25% in of when the price of memory started coming down. So maybe 2 years before that, well, 2 years before that, 8 megabytes of memory probably didn't exist. But 2 years before that, 2 megabytes probably cost $1,000 or more, maybe $2,000 for 2 megabytes. Okay. I remember building computers for a company one time, and this one guy wanted 128 megabytes of memory in his computer, and we thought he was insane. Like, who's this guy trying to impress? 128 megabytes. Oh, you'll never need that. This is like when most people in their computers got 16 megabytes was considered like, 16 megabytes then was like our 4 gigabytes today. If you were really crazy, you did 32 megabytes. Nobody did 128. You had to order the special chips, the ones that had more memory per chip because you only had so many slots inside the computer. Okay, so punchline here is memory used to be really, really expensive. Okay, so since memory was really expensive, back then, programmers had a little bit different mindset. when we were writing our programs, we had to be good stewards of the amount of memory we had, because memory was at a premium. Okay, so just like when gasoline was $4 a gallon, you were probably less likely to just go on joyrides than when gasoline's under $2 a gallon. Make sense? Kind of, sort of the same thing. All right, but probably a couple thousand times worse when it came to memory. So in any case, programmers who wrote these older pieces of software, when they stored the date, the year portion of the date, rather than storing it as 4 digits, 1999, 1998, they stored it as 2 digits. 98, 99. Well, then we hit 2000, which is 00. And the concern was, depending on the software, some, especially software that has sorting, that put things like maybe invoices and stuff like that ordered by date, they were not going to be able to tell the difference between the year 2000 and the year 1900. That makes sense? So now you have problems, as you pointed out, missiles going off possibly and all this other stuff. So there was a big scramble coming into the year 2000 to go back and update all these older programs that use 2-digit dates instead of 2-digit years instead of 4-digit years before the world blew up. Okay, and I actually remember sitting on my couch watching, the new year coming. It was like a 16-hour epic adventures. I was sitting there, and I think, was it New Zealand is the first that hits midnight? And they just had like a still shot on this power plant in New Zealand, and you're just waiting for the sparks to start flying. So I'm sitting there just waiting. I sat there for the whole 16 hours like a nutcase. Nothing happened. It was very disappointing. I mean, it's probably good, but given what I was preparing for, it was kind of like going to an Indiana Jones movie where he just sits there and reads a book. There was no whips, there was nothing, right? Everybody knows who Indiana Jones is, right? I mean, they just made another one not that long ago, right? Yeah, worked out. Actually, it reminds me of a funny joke. One of my friends in grad school, was one of my students. Oh my gosh, I'm getting old. Well, anyways, we were both fat, and we were walking on this track. This is when I taught at Western Illinois University, and he was a black guy. I'm still friends with him on Facebook. His name is Cornelius Jemison. He is a programmer down in Chicago. And he was going on, and I was during the whole slavery reparation fiasco stuff. So he was going on and on about his family deserved all this stuff. And so I made some wisecrack about, I used to be Jewish. I'm Lutheran now, so that's a whole nother story. But I made some crack that it's like, you're complaining about slavery reparation. Us Jews, we're making another Indiana Jones movie. He laughed for about an hour. It was pretty funny. So that got me thinking about that. We're making another Indiana Jones movie. That's where we'll get our money. All right. So in any case, memory used to be really expensive, so old programmers wrote programs with that in mind and tried to minimize the amount of memory they used. Fair enough. All right. So now we're back to our primitive types and need to answer the question of why did we need so many different ways of holding whole numbers? Well, remember, these primitive types came from this language, which then was adopted by this language, which was then adopted by this language, then this language. So these primitive types are still around today because our languages were built in terms of the language before us. Why take the primitive types out? Make sense? Okay, so our languages today, next semester you'll be using Java, and here I'll use Java for some examples, but the tool we'll be using is GameSalad. But our language today supports these older primitive types. But now we want to give some meaning to these. So bytes are signed 8-bit integers. Signed means they can hold positive and negative numbers. Okay? So that means that A byte can hold a number represented as 8 bits. So this is binary. Now we got to go back to that. Converting. Let's see, most of you had 150. Did you do binary to decimal, decimal to binary converting in 150? Briefly? So no? If I gave a quiz on it right now, would it be a problem? All right. So an 8-bit number would be a number represented by 8 zeros and 1s. So the range of 8-bit numbers would be 8 zeros all the way up to 8 1s. Okay? So, as an example, the number 1 in binary, the decimal number 1, is that. The decimal number 2 is that. And here's why. So I'm going to just zero it out here, and I'm going to put some spaces. Okay. So this is the 128's place. This is the 64's place. 32's, 16's, 8's, 4's, 2's, 1's. Similarly, we can say this is the 2 to the 8th place. This is the 2 to the 7th place. This is the 2 to the 6th place. 2 to the 5th place. 2 to the 4th, 2 to the 3rd, 2 to the 2nd, 2 to the 1st. So all the way over here, this is 2 to the 1st place. I'm sorry, no, I'm lying. This is 2 to the 0's place. 2 to the 0's place, 2 to the 1, 2 to the 2, so this is 2 to the 7. All right, so 2 to the 0 power is 1. 2 to the 1 power, 2 to the 1st power is 2. 2 to the 2nd power is 4. 2 to the 3rd power is 8, so on and so forth. Okay, so the way we calculate, if we have a binary number like this, so this is the number 1. I've advertised this as being the decimal or the binary equivalent of the decimal number 1. And the way we solve that is we have 0 times 128 plus 0 times 64 plus 0 times 32 plus 0 times 16 plus 0 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. So you do that sum, you get a 1. The binary version of the number 2, this is 0 times 128 plus 0 times 64 plus 0 times 32 plus 0 times 16 plus 0 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1. That gets us a 2. Plus 1 times 2 plus 1 times 1. That gets us a 3. That's a 4. That's a 5. That's a 6. That's a 7. Make sense how that works? And the thing is, there's nothing magical about this. You already knew this. We're just not comfortable with binary. And what I mean by that is, if I wrote the number 127 down, we're all comfortable with 127. We kind of know what that means in base 10, right? This is 10 to the 2's place, 10 to the ones place, 10 to the zeros place, or this is the 100s place, this is the tens place, this is the ones place. So 127 is 1 times 100 plus 2 times 10 plus 7 times 1. That's 100 plus 20 plus 7, which is 127. Make sense? We did the exact same thing as we did up here, except with base 2, these are powers of 2 down below. In base 10, these are powers of 10 down below. Make sense? All right, now computers, they speak binary. So stuff internally is represented as binary numbers. So a byte is represented as 8 bits. And I said it's signed. Signed means it can hold both positive and negative numbers. Okay? So because of that, the very first bit of that 8-bit number is used to hold the sign, positive or negative. So that means we only get the last 7 bits to hold the actual value. Okay? So a full 8-bit number can hold the values, as I've advertised here, if we're not worrying about sign, everything's positive. A full 8-bit number can hold the values in the range of 0 to 255. Okay? But in this case, we need to hold the sign. So we only get 7 bits to hold value. So our byte can hold positive or negative. So we'll say plus or minus 2 to the 7th power. Okay? Which is equal to negative 128 to positive 127. That's the range of values that a byte can hold. So if you want to store the number 500, it will not fit in a byte. It's too large of a value for an 8-bit signed number to hold. That makes sense? But if you're going to hold a value somewhere in this range, let's say you only needed to count between 1 and 10, a byte's your guy. It's using the minimal amount of memory available to you to store the number you're interested in. A short. Let me actually steal most of this line. I'll just update the parts. A short is a signed 16-bit integer. So that's plus or minus 2 to the 15th. Because again, the very first bit is used for sign. So that's negative 32,768 to positive 32,767. It's the range of values that fit into a short. Much bigger range, twice the number of bits. And we can see that by powers of 2, it goes up pretty quickly, right? All right. An int is assigned 32-bit integer, plus or minus 2 to the 31st. And this is roughly negative 2 billion to positive 2 billion. So this is 2 to the 31st. Let me copy this. Yep. Negative that to positive that. So that's the range of values that fit in a int. Plus or minus 2 billion and change. A long is assigned 64-bit integer, plus or minus 2 to the 63rd. Negative that to positive that. Just leave it at that. We're one bigger here, but in order to do that, I have to expand it out. So just two big numbers. All right. So what is that? So we have 18. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 more zeros. That number. To that number. Take the points off. So this is This is 9 sextillion, 223 quintillion, 372 quadrillion, 37 trillion. Big numbers, okay, but not infinite numbers. We can't come up with too many applications where we need a larger number than that, but we can certainly, as people, understand that it might exist, right? Okay. So that's a long. A char. Now before I write something for char here, we've seen that we have 4 different ways of holding signed integers, positive, negative integers. And we get to choose the one that's the best fit for us. Okay? Realistically today, you always use an int. If it's not big enough, you use a long. I would say you will never see anybody using a short anymore. You might see somebody using bytes, but for a different reason. If they're streaming, if they're writing a program that deals with like streaming video or something like that, where things are coming in 1 byte at a time, it might make sense for them to deal with it in terms of bytes, not for any sort of memory reason. Okay? Because today, we don't really care about memory. It's not impossible for us to run out of memory in our computers, but we don't really need to be very concerned about it for our average computer program. You know, we're not back in the day where, you know, we were talking about 32K costing $10,000. We're in a different day today where RAM costs pennies. Okay? So I would say this guy is probably extinct in modern programming. Byte is not, but it's very rare. Int is going to be the most prevalent. You'll see ints all over the place. And then in the couple of situations where an int isn't quite long enough, you'll see longs. All right? So these are 4 guys for holding integer, signed integers, plus or minus whole numbers. Now, a char primitive type is built for holding characters. Okay, when we think about our memory in our computers, and that guy, the variables are supposed to mimic the way we solve problems. One of the things we like to hold is numbers. Another thing we might want to hold is letters, characters. Maybe the question mark, the exclamation point, the comma, the letter B, stuff like that. That's what a char is. Now the surprising thing here, though, is that a char is actually an unsigned 16-bit integer. Which is 0 2 to the 16th, or 0 to 65,535. Okay, there's no sign, so it's assumed to be positive. Did I do that right? 2 to the 16th should be 65,536. Yep, okay, good. All right. Now, why is it that chars actually hold positive whole numbers? Do we have a guess? Go ahead. Huh? No such thing as negative characters. Now, you've been in a class where I've explained this before.
Yes. Nobody else is answering.
Go ahead.
Well, if they're not numbers, then there's no relevance to positive or negative.
Well, what these guys are made for is holding things that look like. Where am I? There we go. Holding things that look like A or B or the question mark. Stuff like that. These aren't numbers, are they? Those are characters to us. But I'm telling you that chars actually hold them like this. They hold them as numbers. Why is that? Well, we got to go back here to this slide. Computers like dealing with numbers. Computers store everything in binary. Okay, so at some point, it has to be represented in binary and then mapped to the character equivalent for human eyes at a later date. That make sense? So, how many of you have heard of Ascii? Just talked about that in 150? Or you just heard of it before? Okay. What does Ascii stand for? Let's start with that. Not overly important, but if you happen to know it. So this is the American Standard Code for Information Interchange. Okay? And Ascii has 255 unique characters. I'm sorry, 256 unique characters labeled. Is that how you spell labeled, or is there one L? Or 3 L's, 5 L's? Oh, must be 2. All right, labeled 0 to 255. Now, the way this works is the binary number 0 maps to some character. The binary number 1 maps to some character. The binary number 255 maps to some character. All right. Ascii was the standard for years and years and years, but it is blind to foreign languages. Just the American set. And we don't have 256 unique characters in English. So it's actually funny. Rather than supporting some other languages, what did dumb Americans do? Well, we put smiley faces. You've got to have smiley faces, right? Okay. We have some playing cards. If you've ever tried to open up an executable file like in Notepad, something like that, you see a whole bunch of different like weird text, weird stuff. That's it trying to map whatever's in that executable, that binary stuff, to the textual equivalent, the Ascii equivalent. So you'll see smiley faces, you might see playing cards, various other symbols, that kind of stuff. Okay, so we have 256 unique characters we can store, of which we use about half of them, whatever. All right, so this is Ascii. An older language like C supported Ascii. So did C++. Somewhere in this realm, a new standard came about. Anybody know what it's called? Talked about Ascii, but you didn't talk about its successor, Unicode. Okay, it's a universal code. So Unicode, actually, just jump back here. Ascii is represented as a unsigned byte, 0 to 255, as opposed to a signed byte, which is -128 to +127. Okay, so if chars were only needed to hold Ascii, they would be an unsigned byte, as opposed to what I've advertised here as an unsigned 16-bit integer, which is an unsigned short by our definition. Make sense? So Unicode has 65,536 unique characters, covering a large percentage of the world's languages. Okay? Not necessarily all of them, but a large percentage. So it's a much more universal character set, since our software today, is global. You go out and you buy a copy of Windows. Well, when you install it, it asks you what language, and if you do the drop down, there's like 40 languages in there, 50 languages you can choose from. All right. So in any case, Unicode supports 65,536 unique characters. Other than that, it works the same. It stores everything as 16-bit numbers, 16-bit unsigned integers, and then each of those integers maps to a character when you actually want to display it to the screen. Okay? So the char primitive type holds these guys as 16-bit numbers, but it stores them, or it displays them as the character equivalent at runtime when we actually do the mapping. That makes sense? All right. Let me give you your first assignment, a little warm-up assignment before we get to programming stuff. Okay? I'll put it on Angel here in a second. I want you to write a 2 to 3 page paper discussing the Y2k problem. Discussing the Y2k problem. What was it like leading up to it? What was it like right after? And maybe even talk about what kind of jobs were created as part of the Y2k problem. Part of what you might read in there, just as a kind of a heads up, is you had a technology bubble that came out of around the year 2000. That was because there was a lot of jobs created as part of the Y2k. Then we used those folks for new projects. Then companies, the stock market took a hit. Company had to lay off a bunch of people. All right, so 2 to 3 page paper on the Y2k problem. And that's due on Monday. Then we'll finish this up, and I'll see everybody then. I'll put that on Angel now.